Hello, good morning, everyone. I want to welcome you to my lecture today. Of course, today, this week, we're going to continue with clustering. I remember on Friday, I introduced you to K-means, okay, algorithm for clustering. Okay, so today, I'm going to walk you through another form of algorithm for partitioning clustering that we call K-Medoids and hierarchical clustering as well. So in the outline, just like the way we did that, I walk you through the algorithm, the application, evaluations, and drawback for K-means. I'm also going to do the same for K-Medoids and hierarchical clustering. Okay, so let me remind us that we got some common algorithms for hard clustering. We all know what hard clustering means. Okay, the type of clustering where we actually want to partition objects into distinct clusters, non-overlapping clusters. And of course, one of the algorithms that we use for that is K-means clustering, and we did that on Friday. Now we have K-Medoid that we're gonna walk you through now. We got hierarchical clustering, and of course, we got density-based spatial clustering of application with noise. So right now, I'm gonna go into K-Medoid. You know how K-means work. Now I'm gonna start with K-Medoid right now. But before going into K-Medoid, I really want you to see the kind of connection between the K-means and K-Medoid. Okay, so in K-means approach, we actually randomly select numbers from data set. Okay, maybe, well, of course, in advance, we decide on the number of clusters that we're going to have. And by trying to go into the data set pool, okay, identify, maybe like choose a certain number of data point randomly. And after doing that, then we assign the remaining object into the cluster that we feel very close to data point using the similarity or dissimilarity of distance. And we update. After the assignment, we update by trying to find the mean of each cell center. We find the mean. The mean of a cluster, the mean of a cluster is actually called the centroid. Okay, the mean of a center of a cluster is called the centroid. And after that, having the average, then you reassign again using the updated average. Now, you're actually going to stop your assignment if there is no any significant difference between the means that you have updated, and you're actually going to say the algorithm has converged. But let me tell you this. Situation where there's an outlier in the data set, K-means is going to be highly sensitive to outliers, and we cannot trust K-means whenever outlier is in a data set. Outlier, according to Benkamp in 1982, is a particular data point that is not consistent with the rest, and in statistical analysis and in machine learning world, we normally try to see how we can deal with outlier. So when you're talking about partitioning clustering, okay, K-means algorithm is not a good idea if outlier is present in your data set. And that is why we need a variant. We need a variant of k-means. One of the variants of k-means that can be used if we suspect an outlier in data set was actually proposed in 1987 by Kaufman and Russell. Okay, we call that K-Medoid. Okay, so K-Medoid, also called PAM, which means we want to partition around medoid. We're not partitioning around me anymore. So what do we mean by medoid? Do you know that K-means and K-medoid, they have the same process? The only difference between K-means and K-medoid is that in K-means, after the initial assignment, we compute the mean of each cluster, okay, then we reassign. But in the case of K-medoid, we don't compute the mean, so of the center. We pick one of the observation. We're using the actual data point, not the center, because the center may not be the actual data point. Okay, that's what we call medoid. The actual data. So when we choose a particular data point randomly to serve as the center, that is going to be called medoid. And what we're going to do, we compute the total cost associated with choosing that. Then what we're going to do, we drop it, then we choose another, we swap with another point. Okay, when we swap with another point, we're also going to calculate the total cost. Now, situation where the total cost is less than the previous one, of course, then because the intention is to minimize the total cost. And I'm going to demonstrate that to you. Now, let me say this. Whether you are working with k-means or k-medoid, we got objective function. I'm going to say that again. Whether you are working with k-means or k-medoid, we got objective function. The objective function with k-means is is actually to minimize the sum of square deviations. Okay, minimizing sum of square deviations of the data point from the cluster center. But when you talk about the objective function in the K-medoid, is to minimize total dissimilarity that I'm trying to show you on the board. Okay, this is the objective function for K-medoid. I'm going to say that again. The objective function for K-medoid is to minimize the total dissimilarity or the total distance between the medoid. What do I mean by the medoid? The particular point that we choose that represents the cluster center. That's what I mean by that. Okay, so but for the k-means, okay, for the k-means, the objective function is written in a way to minimize the sum of square deviations. Okay, sum of square deviations of the object from the cluster mean. Okay, now because of that, I'm actually going to say the two objective function in the K-medoid. Okay, K-medoid use, if you want to calculate the distance, okay, the K-medoid use Manhattan distance, which is the one in absolute time, Manhattan distance. The Manhattan distance is L1 norm, while the K-means use Euclidean distance. Euclidean distance is L2 norm. So the L2 norm is different from L1 norm. L2 norm is talking about something squared. Okay, sorry, L2 norm is talking about something squared. But L1 is talking about absolute. Okay, it's talking about absolute difference. And you remember, and that is the reason why objective function of K-means and objective function of K-medoid, they are converse functions. You remember what we did under converse function? I'm going to say that again. The objective function of K means, okay, the objective function of K-Medoid, they are converse function. But let me tell you this. They are converse function initially. But because of the algorithmic process, okay, algorithmic process induces non-convexity into the process. I'm going to tell you how. Because when you're working with K-means or K-Medoid, you will have something to do with cluster assignments. Cluster assignment induce non-convexity. And not only that, you need to update your cluster. We update centroid. In the case of K-mean, you update medoid. In the case of K-Medoid, because of the cluster assignment and the updating that we do, okay, induces non-convexity into the converse function of both K-means and K-Medoid. And that accounts for the reason why with this, we're only going to get local minimum. There's possibility the algorithm with the K-Medoid and with the K-mean get trapped in the local minimum. Why? Because even though the two functions, they initially converse, but because of the algorithmic process that induces non-convexity, okay, there's possibility that the algorithm get trapped in the local minimum. And what do we do to address that? If we address that, and that is why we're actually going to have more than one random assignment. You saw in the code that I put n start equal to 25, right? If you K means the coding how last week, you saw n start equal to 25. Okay, we want to choose a reasonable high values that would make sure they don't get trapped in local minimum. Okay, we choose between 25 and 50. When you choose more than 50, the law of diminishing return will set in, where that may not achieve anything. So I'm just trying to let you know about the two. Now, this is the process of the algorithm for K-Medoid that we also call partitioning around Medoid. Okay, giving K means you actually need to decide on the numbers of clusters, the same thing that we did in K-means. Then you randomly pick instances as initial Medoid, then you assign each instance to the nearest Medoid, you calculate the objective function, and what we intend to do is to minimize the sum of the dissimilarity of all instances to the nearest Medoid. I think I'm actually, and let me also tell you this, we swap, I told you, when you use when you actually use a data point as a Medoid, we swap that data point with others. And I'm going to demonstrate to you how that happens. We calculate the cost. When I use the data point as a Medoid, I calculate the cost. When I swap it with another data point, we also calculate the cost. We're looking for a Medoid that will actually give us the total minimum cost. Now, if you want to know the time your analysis will run, that is, is k into n minus k squared, where k is the number of clusters and n is the number of your data. So, because, if you really want to be able to know on time, like ahead, how many times am I going to wait? Now, please pay attention to this. I want to demonstrate now with two-dimension data. Please pay attention now. I'm still going to walk you through how to do this in R, but I first want to demonstrate to you how K-Medoid work. Now, I got 9 observations right now, and they are bivariate, X and Y, 5, 6, 4, 5, 4, 7, 6, 7, as you can see. Now, I want to apply what I call the K-Medoid now process. And what I did first, I randomly select 2 pairs. The first one, 6, 7, okay, and the second one, 7, 9. You can see in 2 different. So I'm going to put the 6, 7 here in cluster 1 and 7, 9 in cluster 2. Please pay attention. And you know what I'm going to do? I'm actually going to be looking at the distance. Take a look at it. 5, okay, minus 6, then 6 minus 7, the absolute value. I'm actually going to add it, and that's going to give me 2. Please take note of that. I will do the same to this guy. Okay, which one give me the minimum value? 2. Is it cluster 1 or is it 2? Which one is minimum between 2 and 5? That would be 2, right? So because 2 is the minimum, where do we have that 2? In cluster 1. That was why I put cluster to be C1. Is there any question on the first one, the first row? Any question on the first row? Everybody good, right? Okay. Now you're going to go to the second row and repeat the same. And at the end of the day, you know, when I continue to do that, okay, I was able, if you take a look at the cluster here, okay, it means I only have 4 clusters and I mean 4 for cluster 1 and 3 for cluster 2. Don't forget, I have 9 observations in the first place. Of course, the other 2 are the one that I use as my Medoid. Does that make sense? Okay, now when you take a look at this now, we need to update. Now, this is, if I want to update, I need to first calculate the total cost. I want to find the total cost for C1 and the total cost for C2. Okay, and this is the formula if I want to do that. Now, the total cost for C1, I need you to pay attention. Please pay attention. If you don't understand, ask me a question. Take a look at this guy. Those are the ones that we classified in cluster C1 and here in cluster C2. The one in red, C7 and 7, 9, they are the Medoids for each cluster. Now, what I'm going to do now, I need to add the cost together. Now, some of you may be wondering, where do I get 2, 4, 2, 5? You're going to come here now. Okay. You're going to come here now. Okay. And I needed to pay attention. Okay. When you take a look at C1. Okay. So for which one is the smallest? Here. The smallest. Here. The smallest. Here. The smallest. When you compare across, do you see where I get 2, 4, 2, 2, 4, 2, 5? Okay, that is the cost that I'm actually that I'm adding here. 2, 4, 2, 5. Then I'm also going to go into the cost of the other one. Okay, for cluster 2, C2. Okay, now for cluster 2 right now. Okay, I want to focus on C2. Focus on this C2 and focus on this C2. So right now, okay, this is the smaller of this 1 and 2. Okay, this is the smaller of this 1 and 4, and this is the smaller of this 3 and 4. So because of that, I'm actually going to have 1, 1, 3, right? 1, 1, 3. Okay, now the 1, 1, 3. Give me 1 second. The 1, 1, 3. That was how you got this one. Then when you add them up, the total cost of choosing those Medoid 6 and 7 and 7 and 9, the total distance is 18. Total cost is 18. Now, the next thing we're going to do now, we're going to swap. We're going to choose another one. Okay, the one we choose before, we're going to choose a different one this time around. We're choosing 5, 6. Okay, so if you take a look at what we are choosing now, we actually going to retain for C2 and we choose a different one for C1. So we're using O1 to replace that and we complete the whole exercise. And as you can see here, this cluster O, we're not going to use C1 anymore. Cluster O is representing the former C1. Okay, then I'm going to compute the total distance again. Now, when you take a look at the total, the total cost, we're going to compute the total cost again. If you take a look at this total cost, this time around, 17 is less than the total cost of 18 that we had initially when we used the previous Medoid. Okay, so, and that was why I said the cost of swapping of Medoid C1 with 0 is with O is which is S current total minus the previous one is less than 0. Okay, so swapping C1 with Z0 will give us a better clustering because the lower the total cost, the better the quality of the clustering. Does that make sense? Okay, that is the way it is. But you know what? Yeah, imagine a situation where we got a huge number of data set. We don't have time to do all of this. Okay, I'm going to show you how we do that now. Okay, but I'm first going to walk you through advantages of that. It's simple and understand and easy to implement. And of course, it's very fast and converges in a fixed numbers of steps. Then the major reason why we use K-Medoid because it's less compared to the K-means because it's less sensitive to outliers. You know, I saw some kind of reaction from some student, not in this class, comparing K-Medoid, believing K-Medoid is K-median. They are not the same. Okay? When you are using K-median, that means we are using a median value of the, but this is, you are using the real data point, the data point among the observation. Okay? So it's sensitive to outliers. That's why. And what is its disadvantages of this? Let me tell you this. It is not only K-Medoid that has this disadvantage. Okay, even K-means. K-means or K-Medoid and the hierarchical structure, they are not for non-spherical shapes. They are only for spherical shapes. Okay? So the moment you have you have a complexity, if you have arbitrary shapes that is other than spherical, okay, it's not going to work great. Okay, and it may give different results for different runs on the same data. Okay, so now how do we do it in R? You know what I want us to do in R? Of course, the assignment that I'm actually going to release today was centered on a lot of stuff where I wanted to use a particular data set in R where you're going to compare the K-means with K-Medoid and so on like that. I needed to pay attention because on Friday we've used this data set, USRS for K-means. I want us to use it for K-Medoid as well. And we want to see whether they actually going to take a different decision. Okay. But let me tell you the situation where there's no outlier, K-means and K-Medoid, we actually give approximately the same results. Does that make sense? Okay. Now, just like what we did in the K-means, you need to load all these packages. Okay. You need to load all these packages. Then this is the way to get your data. And don't forget how we deal with missing values in data set in our na.omit. Okay, you have to be able to remove rows with that. Then we scale our data set. Okay, in case we have data set, we have features that have different units. Okay, we have to scale that. Now, if I want to see the 4, 6, I'm going to write add into that. Okay, I'm seeing that this data set is about we got crime variables collected across states in the United States. Okay, this is the 4, 6, and what you see now are standardized values. Okay, they are standardized values. We have information about the murder per 100,000, the assault per 100,000 in the state, the urban population, percentage population in the state, and 100,000, per 100,000 case of rape. Now I need you to pay attention when you are dealing with K-Medoid. We use, you can see I specify Euclidean, right? Okay. Now, and if I actually if you take a look at this guy, that is if I want to look at the elbow, okay, that will give me, because the elbow actually will give us we plot within variation the average expansion against the number of clusters. Of course, we all know for cluster 1, where we have not grouped the data, we expect the variation to be much. And the more you increase the cluster, then you expect the the total variation within cluster to be decreasing. But we don't want to waste the number of clusters. We don't want to waste that. We need to be able to see the convergence point. Now, because of that, we consider able. If you take a look at this now, okay, you're actually going to see, I started seeing the able from here. If you take a look at all this, it's obvious for k equal to 1, okay, for k equal to 1, that is what has the highest, right? K equal to 1, k equal to 1, you've not partitioned anything at all. The object are still heterogeneous. And as you are increasing the number of clusters, you actually see a decline in the total within sum of square. But we don't want to waste the number of clusters, okay? And with the able method, we are, this, we be able to see where we actually going to say convergence has taken place. Okay, so right now, the next thing that I actually want to do, because of the fact that we got different kind of evaluation method that we can rely upon. We can also look at the gap statistic. The other time, the same criteria that we use in evaluating K-means algorithm, we also use that for K-Medoid. Okay, so right now, okay, I specify all this. And if you take a look at this, inside my specification, I put the maximum cluster to be 10. And at the end of the day, when I actually sketch that, look at what I have. Okay, so this is also pointing at 4. You know why it's pointing at 4? Don't be deceived by this. That is 3. It's not. Because you know why? Something that is increasing, right? It's increasing. But when you get to this point, what happened? It start going down. So that point is where k equal to 4. Do you see that now? Okay, so it means the gap and the able actually suggesting the optimal number of cluster to be 4 here. So take a look at that. Okay, now if that equal to 4, then it means we're actually going to perform our final model for K-Medoid will be when k equal to 4. And don't forget, I said you should set seed. Okay, we're actually going to set our seed, and this is the result that we have, okay, for the k for the K-Medoid. Now when you take a look at what I have right now, we're only giving you the first 4, okay, for Alabama, Michigan, and so on, like that. Now we can generate the cluster. They say it's 4, right? Which is this guy here. I think I remember we also get 4 for K-means last week, right? Yeah, so they agree here. Now, I'm actually building my final model, okay, based on that 4. And this is what I have. Okay, if I have this is just showing me the first 6. Please, I need you to pay attention because interpretation matter. Okay, interpretation really matter. Let me interpret 13.2 in Alabama. It means the average number of murder in Alabama per 100,000 is 13.2. That's for Alabama. Okay, assault for Alabama is 236 per 100,000, and Alabama has 58% of urban population, and Alabama has 21.2 on average per 100,000 for rape, and Alabama is actually clustered, is in cluster 1. These are just the first 6. Don't forget, we did that for the 50 states in the United States, and they were classified into 4 clusters. Okay. Now, when you take a look at this now, the the gap statistics for that, you can see equal to 4 clearly, right? Okay, this is the highest it goes before it starts decreasing, right? That's K equal to 4. Now, and I want to do something here. I'm comparing the gap statistics for K-means that we did last week and the K-Medoid. This I needed to pay attention. Okay, the gap statistics for the K-mean, the first one here. Okay, this is let me do this. This is for the K-Medoid. Okay, why this is for the K-mean. Please, I need you to pay attention. For the K-Medoid, you can see that 4 clearly, right? And for the K-means, of course, it's still 4 if you take a look at this point. Because along this point, it's decreasing down. Okay? They agree. The gap statistics for K-mean and K-Medoid agree on the optimal number of clusters. Does that make sense? Okay, is there any question before I go into hierarchical clustering? Is there any question on K-mean, K-Medoid? Okay, let me tell you, I want to use this opportunity to introduce you to hierarchical clustering. Hierarchical clustering is very, very crucial. It does not require what I call the number. It doesn't require you to predetermine or to state your number of clusters ahead. With the K-median, with the K-medoid and K-means, okay, you need to specify the number of clusters. But here, this is a deterministic approach. Hierarchical clustering does not have an objective function. I'm going to say that again. Hierarchical clustering does not have an objective function. Okay, but what do we use as a criteria? Then I'm actually going to show you what we use as a criteria. We call it linkage. We got different kind of linkages. So I welcome you to hierarchical clustering. Okay, and in hierarchical clustering, we actually going to produce. Let me just tell you what is the benefits hierarchical clustering actually brought into partitioning process. It will enable us to investigate, to see relationship that exists between clusters. In the case of K-means and K-medoid, we're not able to actually see that. Okay, and that was why I said it give the answer I give is somewhat random. It depends on random initialization we started with, and it does not require specified choice of cluster. Okay, and there are 2 types of that. We have a bottom up and we have what we call a top down. But the one I'm going to showcase today is bottom up, where we build, from the bottom to the top. But let me first show you the manual way. Like, I got these 5 objects, right? Having these 5 objects, I want to actually want to use hierarchical clustering. Some of you may not know the significance of this. For instance, if you have been to, if you go to downtown Minneapolis or downtown Chicago or downtown New York or downtown, all those major cities, you're actually going to see a lot of tall buildings, right? On the tall buildings, what if they want to put what we call phone, cell tower? They want to put, phone cell tower on that. They want to make sure buildings are actually enjoying consistent coverage, right? In that situation, they're actually going to use this hierarchical clustering, where they're going to consider, buildings that are, very close to each other, buildings far from each other, and stuff like that. The hierarchical clustering is very, very crucial in that regard, in building those clusters. Now, take a look at this. I got 5 objects, and I want to use the idea of hierarchical clustering. I'm actually going to start with 2 objects that are very that are closest, which is that A and C, right? I'm going to start with that. Then the next closer one is D and E, and I need to see what is going on here. Please pay attention here. You can see initially A and C, they're very close together, right? We put them in a cluster, and we now realize that B was close to the cluster. Okay, we put them inside. So in that situation, that is nested. It's like one is nested in the other one, AC nested in B. Can you see that? We're not able to, witness stuff like that when we talk about K-means and K-Medoid. Now, lastly, we're now going to have this. At the end of the day, all of them will be in a major cluster. Is there anyone who doesn't understand that? Okay. We normally draw a visual plot that we call dendrogram. We can draw that based on what we have. Take a look at that. Initially, don't forget, we started with AC, okay, as the most closest, right? AC. And because of that, we actually sketch this for AC. And after AC, what is next to AC is B. B is nested. AC is nested in B. And that's why you see it. You see that AC nested in B. You can see the B is the bigger one, right? Because here, the B is the bigger one and AC is nested in that. And if you go to the other side, you got a DE, right? Okay, this is why we have a DE separately here. And all of these are nested, maybe in something that we did not mention, in the whole. I'm seeing this as maybe a Times Square in the New York that have a lot of buildings where some are nested, stuff like that. That's a dendrogram. Okay. Now, let me tell you this. Because of the fact that hierarchical clustering does not have an objective function, but we need a criteria that will enable us to know where to stop when we draw an hierarchical tree. Then we need a linkage. What is a linkage? Linkage is the distance between 2 clusters. Okay, the distance between 2 clusters. So because of that, we're actually going to have 4 different type of linkage, which I'm going to summarize. Okay, single linkage. The single linkage is that minimize the smallest distance between 2 objects in clusters. Then we got complete linkage. Complete linkage minimize the maximum distance between 2 clusters. And let me tell you this. We normally have issue with single linkage. Okay, we have issue with complete linkage, and to strike a balance, we use average linkage. Okay, now take a look at what I'm trying to show you now. Oh, give me a second. If you take a look at what I'm showing you now, okay, this is single linkage. Why? Because we are only considering, can you see that? We want to minimize the distance between two clusters that are the most closest. If I'm actually looking for a linkage that will work, if I want to put a cell phone on a building, on a tall building in the New York City, I'm not going to use single linkage. Okay? Because the single linkage will lead to a situation where the clusters are going to spread out. Okay, because you want to minimize the distance between the closest. But take a look at this. So on the single linkage, if I draw the dendrogram, I just wanted to see the difference between the criteria you use for single linkage. Take a look at what you see here. You can see how many blue color do we have? 5, and yellow colors are many. And this, what you have here is a corresponding dendrogram. Okay. Now, if I go to complete linkage, what do you see in the complete linkage? The numbers of blue is more, right? Because the complete linkage make an attempt to minimize the maximum distance between clusters. And that is why for New York City, okay, they will want to minimize the maximum distance, okay, between the tall buildings in such a way that the cell phone, or that they want to put the cell that they want to put on the building, on the tall building, will be consistently, the buildings, they're actually going to have what I call enjoying consistent coverage. Okay, now, okay, this is the average one. The average one is to strike a balance, because with a single linkage, that will lead to a chaining problem. With the complete linkage, that will lead to overcrowding. And can we strike a balance? Then we use the average distance. But do you know issue with the average distance is interpretation is lost with the average distance. Okay. Now, this is the average distance. You can see that again, the average distance brought even one additional column. If you take a look at this, okay, and look at the dendrogram, okay. And let me also tell you this. Look at this dotted line. We normally want to create a height, okay. That very height is the maximum distance we can tolerate for two objects in a cluster. Before we can classify them into a cluster, the maximum distance we can tolerate. And that's why we normally cut the tree. Okay. Now, I think I just talk about, the single linkage has suffer from chaining. The complete linkage actually that avoid chaining but suffer from overcrowding. Okay. Why the average linkage will strike a balance. And I wanted to see, take a look at the three. They are not the same. Look at the single, when you use complete, when you use average. There's another one that we call ward, W-A-R-D. Okay, that very word minimize variance within clusters. I'm going to say this again. The single linkage minimize minimal distance of pairwise, okay, between two cluster. The complete minimize the maximum. Then the average minimize the average distance, but word minimizes variance within cluster. Now that you understand that, I quickly want to go. Okay, this is what I was saying the other time. Okay, where should we place a set towers? These are tall buildings. Suppose we wanted to place a set towers in a way that ensure that no building is more than 3,000 feet. That is the cut that I mentioned the other time, that we don't want it to go over. Okay, we believe that the moment it is it's less or equal to that, we'll be able to reach the maximum number of clusters. Then what linkage do we need to use? Is it going to be complete, single, average, or word? Okay, for a place like this, it should be complete linkage. Okay, now I quickly, we have a lot of computational issue with hierarchical. The memory, for storage, n squared, the n, you have n by n, the similarity matrix, time requirement, n squared multiplied by log n. This is just for you to be able to know the time for the algorithm with the hierarchical to run. Now, I need you to pay attention now. How do we do this in R? Okay, let's get started. Take a look at that. If you take a look at this guy right now, give me 1 second. Okay, if I want to start with hierarchical, I need to specify linkage. You can see average, single, complete, and word. Because I want to be able to know which linkage am I going to use to curate my hierarchical tree. Okay, that is what that code is talking about. And the second code, I want to focus on agglomerative, okay, the one that I'm actually going to build from bottom to top, because we also are decisive, okay? So now this is my output. Oh my God, look at the output, comparing the linkage we're going to use. The one that have this highest value is the one that we're going to use for our data. And which one has the highest value here? Word. What did I tell you? Word minimizes variance within clusters. Complete minimizes, the maximum distance. Single minimizes the minimum distance, and average strike a balance. So right now, we're gonna use word for this data set. Now you can see right now, I'm still using the same data set on USRS. What do you see? What do you see now? I actually want to use the method is word, the linkage, because I choose that from the criteria. And this is to draw my dendrogram. Okay, I'm gonna draw my dendrogram. This is my dendrogram now. Okay, what you see here is the variable of interest height, and what you see here are the city, the state in the United States. I just wanted to tell. So this height is just talking about the height of the dendrogram. Does that make sense? Okay, now the next thing you're gonna see right now, can we also have a way to evaluate an hierarchical clustering, just like the way we did under the K-mean and the K-Medoid? Okay, take a look at that. What is K? Can somebody tell me? K equal to what? Here. Okay, good job. It's 4. Okay, now K equal to 4. The same data set. It's like they agree. They agree with the K-Medoid, right? They also agree with the K-means, right? Now, I'm actually going to apply, look at that, to compute the distance, equilibrium, my final module now. My final module, I'm choosing word, right? Okay, now, at the end of the day, I'm having this. This is the result for the hierarchical. This result is very close, more or less the same when you compare that with the K-Medoid and the K-means. So which means in the assignment that I'm actually going to release today, I'm going to give you some data set. I'm actually going to ask you to compare the K-means, the K-Medoid, and the hierarchical. Okay, so take a look at that. Okay, now this is the mean value for each cluster. Okay, the mean value, you can interpret that. What if they ask you to interpret that? Okay, the mean number of murders per 100,000 among the citizens in cluster. Now, if you take a look at this, he has subdivided all the states in the United States to cluster 4. Okay, and this guy here is not interpretation for murder for a particular state, but for all states classified in cluster 1. Does that make sense? Okay, that is what I mean. What is next? What is next? is, you know, when you look at K-means, K-Medoid, and hierarchical clustering, all of them, they are for spherical shapes. Okay, they will struggle with non-spherical shape. And that is why what we're going to do on Wednesday, we're going to talk about density-based spatial clustering of application with noise that's actually going to perform well when we have a non-spherical shapes. Is there any question for me before I go today? Is there any question? Okay, make sure you all stay safe and have a lovely day. Bye for now, everyone.